Okay, welcome back to another video. I wanted to show you guys this one, as it has a lot of good integral information on here in the second fundamental theorem of calculus. So these questions can be a little bit intimidating, but I think it helps to label the graphs. When you have a problem like this, and here you've got this function over here, and they're telling you that that's f, and it's defined on the closed interval from 1 to 7, and then they're defining h right here as the integral of this function f of t dt, and then you see the x up in the numerator, or excuse me, in the limit of integration right there. So hopefully that'll key you in on the fact that you might be using the second fundamental theorem of calculus, which says that the derivative of h is just going to equal, if you take the derivative of the second integral there, or the integral listed, f of t of dt. Well, if you think about it like the derivative and the integral are opposite operations, I guess you will, in calculus, then that kind of cancels out, and it leaves you with the fact that the first derivative of h is just equal to f of x. So this graph f is also equal to the derivative of h. So that's maybe a helpful thing to write down over there. Alright, so now that we have a little bit of understanding of that, let's go ahead and answer part A. Part A says find h of 1. Well, that's simply right off the graph, right? So h at 1 is this point right here, which is equal to 1. So there's not really any justification necessary on that. Just want to see if you can pick that off the graph. Well, actually, that's not true, is it? Let's take a look at this a little bit more here. It says find h of 1. So h of 1, I got mixed up. I thought that was the derivative. So h of 1 would be like me plugging in a 1 right here, right? So it doesn't matter what the integral is, because we don't really have any ability to find that because we don't have a function, we just have a graph. But notice whenever you have the upper limit and the lower limit of integration the same, that no matter what the function is, it's going to equal 0. So you can just simply say that that's equal to 0 right here, and you should be good on that one. Alright, the next part says find h prime at 4. So based on this little definition that we have right here, all we have to do is go to 4, and that's where we just need to look at the graph. So h at 4 is this dot right here, and it has a value at 2. So I guess you could make a statement about h prime of x is equal to f of x. Therefore, h prime of 4 is equal to 2. Alright, so right there we've burned through a couple questions, parts of this question pretty quickly. Alright, part C says, on what interval or intervals is the graph of h concave up? And then it wants us to justify our answer. So, well, when is h concave up? H is concave up when the second derivative, when h double prime is greater than 0, right? Well, we already wrote this down up here, that this graph f is equal to the first derivative. So to find the second derivative where it's positive, we just need to go analyze the graph and notice that here our tangent lines would be negative, right? And we have positive slopes in two different areas. We have a positive slope here, over in this area, and from 6 to 7, right? So it's going to be concave up in those two green sections there. So for part C, we can just write that h double prime of x is equal to f prime of x, and h double prime of x is greater than 0 on 1 to 3, on 1 to 3, and from, looks like 6 to 7. And that should pretty much satisfy that part of it. Yeah, I don't think we need to talk any more about that one. I think we've justified it okay, other than the fact we haven't said that we didn't actually write the fact that it's concave up, because we could say therefore the graph is concave up. The graph of h, the graph of h of x is concave up. Don't abbreviate, but I will. H of x is concave up on the above mentioned intervals. Okay. Alright, let's take a look at part D. It's asking us, not directly, but it is asking us pretty directly. It says find the value of x at which it has a minimum, and they're talking about an absolute minimum on this one, right? A couple of clues. One, they say on the closed interval from 1 to 7. So if we're looking for an absolute minimum, we have to include the endpoints and any relative minimums, right? So let's see if we can make some sense out of that. Let me go grab a pen here. So we're going to look at a sign chart here for the first derivative, and we're looking at h, and I keep writing f, I'm sorry. So we have h of x, the derivative, which is f of x, right? And we can only look at it from 1 to 7. And don't know why I put two little marks here, because it looks like it only crosses. Looks like it only crosses at equals 0 at 5, correct? And it looks like it's positive. It's positive until you get to 5, right? And then it turns to negative here, right? So is there a relative minimum on that range there? Turns out that this is a relative max. So I guess all we need to consider is the endpoints. So let's see if we can analyze what is h of 1. We already know h of 1 from the above part is equal to this, right? F of t dt, which remember is equal to 0. So h of 1 is equal to 0. And then let's talk about what's happening here. Well, if you start off at 0 and this thing is doing what right here? It's increasing, right? Because this function is positive here, which is the derivative of h. So it's positive there, so it's increasing until it gets to 5, right? And it looks like this is a pretty substantial area in comparison to this area down here, this green area that I'm drawing now. So if you keep increasing, this value is going to be getting larger and larger. So perhaps it's up to the value of 6. And then from 5 to 7 in that negative area, the value is going to start coming down from that arbitrary number that I just said, 6 I believe it was. So to me it makes sense that at 0 it's going to be smaller than it is at 7. So let's take a look at how we're going to justify that. I guess we could say that h of 7 is equal to, from 1 to 7, of f of t dt. And we could say that it's greater than 0, and we can justify it because we could say the area between are in the intervals of 1 to 5 is positive, and the absolute value of the area of that area is greater than the absolute value of the area from 5 to 7. Which is negative. So from there we could justify it by that. Basically, there's more area above the x-axis than there is below. So another way to say that might be to say something like this: from not 0, but from 1 to 5. From 1 to 5, f of t dt is greater than the area under the curve from 5 to 7, and that would also justify it. So to finish up, make sure you always state the answer in simple terms. Say, so h has an absolute minimum at x equals 1. And note, we don't know exactly, well, we do know that's equal to 0 in this case, but we have no way of quantifying exactly what is the value at h of 7. I just know that it's greater than 0. So anyway, I hope this was helpful, and good luck with studying for the free response.